I've got my helper with me today. This is Caroline, and we are playing with magnets. And we are going to talk about magnets, how they work, how we use them, and how it's not magic, it's science. So the thing that you probably already know just from being alive is that magnets have two ends. They're what we call polarized. They have a north pole and a south pole. And those two ends, just like our charges that we talked about, if they are the same, they will push each other away. They'll have that repelling force between the two of them. If they're the same, then they're going to attract. Yeah, we'll have candy in a second. So like will repel, unlike the different poles will attract each other. Now there's a lot of ways of making a magnet. There are some magnets that form naturally in the earth. Hematite is a mineral that you can find in the earth that is a natural magnet, and its molecules inside of it aligned with the Earth's magnetic field as it was cooling from a lava state. But a lot of our magnets that we use, like these that I got at the craft store, are created magnets. They're created in a factory that way. And to create a magnet, we do charging, well, not charging, it's magnetizing by induction. Just like we had charging by induction, where you create it in a electric field, you create a magnet in a magnetic field, and those molecules line up and become permanent, and they become stuck that way. So these are created in a warehouse like this. You had this material that they melted. The molecules inside this metal are polar, and so all they had to do was line those molecules up and freeze it that way, so that they are stuck. Now you can create temporary magnets. If we put this paper clip on this magnet, then it can turn around and become a magnet itself. It can pick up other things. Those are temporary magnets. Metals are really good at being temporary magnets because, just like we talked about with electricity, that metallic bonding, those electrons are able to change shape and line up north and south. Once we take the paperclip out of the magnetic field, though, it loses its magnetic effect. It's not magnetic anymore. It's only magnetic. It only has those properties when it's in the presence of that field. A lot of magnets are being used today. We have some examples up here on the screen. One is the maglev train, magnetic lift train, and it works off of the property that causes magnets to repel each other. You've got two magnets, one on the train, one on the track, and they are like poles, so they're pushing against each other, and the train is basically just floating on air, being pushed by that magnetic field. Your credit cards, they have a little magnetic strip on the back, and you have like north and south pole codes basically imprinted into that strip, and whenever your card reader reads the back of that card, it will read the pattern of those north and south poles. So that's why they tell you not to get your credit card near magnets. I'm trying not to, so that you don't scramble that code and mess up your credit card. The big machine here that people lay on, that's a magnetic resonance imaging machine, and it's a medical technology device that lets us see inside the human body without harsh chemicals or gamma rays. It just uses the properties of magnetism. And then you see the junkyard down there. That giant magnet will pick up and help sort metallic objects in junkyards, and that's just a really big giant magnet. The area of influence around a magnet, that area that we'll feel, is called a magnetic field. And we can represent it with magnetic field lines a lot like we represented electrical charges with electric field lines. These are very, very similar. Your magnetic field lines will always form closed loops from the north to the south. She's showing you her candy. It's about to get sticky around here. So they're going to form closed loops that go from the north to the south. You can kind of see it here. Notice your force is a vector. It's got a magnitude and a direction. So you notice it coming out from the north, looping around and going into the south. And if we were to put those iron filings on top, it would look like the picture there on the right. You have your vectors making complete loops from one end to the other. Now there is a connection between the two, other than just the normal charges and north and south and positive and negative. There is a very close relationship between magnetism and electricity. And a scientist named Hans Christian Ørsted noticed this when he was trying to make a compass line up in the same direction as an electric current. What he noticed was that instead of lining up, it turned perpendicular. And he figured out that a compass, relying on the magnetism, the magnetic field of the Earth, except here it's in the magnetic field of your experiment, a magnetic field is perpendicular to the direction that a current flows. So we notice that there's magnetic field around a wire that is carrying current. If you notice the wires going down the highway, there is a magnetic field around those wires. It is not noticeable to us. You don't notice like your keys being sucked up toward the power lines, but there is a magnetic field around them. And the strength of that field is proportional to that current. So that is an actually strong magnetic field through there. He also noticed that if you reverse the direction of the current, if you have it flow the opposite way, the compass needle also swings around and reverses direction. So the north-south is related to the direction of the current flow. Now the picture down there on the right, the orange line is a wire with current flowing through it, and the dots going in the circle are what your iron filings would look like if you sprinkle them around. You notice that instead of the iron filings lining up in a circle around our bar magnet, it's lining up in a circle around our wire. So from that, we came up with the first right-hand rule. Now there's more right-hand rules, but we're going to kind of stop here with the first right-hand rule. And that says if you take your hand, your right hand, and wrap it around to kind of give a giggle sign, if your thumb is pointing in the direction of your current, if the current is going this way, then your fingers are pointing in the direction of your magnetic field. This is north pointing to south. And so we can notice, we can predict the way that our magnetic field is going to line up based on the direction that our current is flowing. So the relationship between the two has become very beneficial to us. We can use electricity to create magnets, which is how a lot of these work. The picture from the junkyard of the giant circular magnet picking up all the car parts, that's what we call a solenoid or an electromagnet. We can use a wire in a closed loop. We'll wind that wire around and around and around into a big loop, allow the current to flow through, and then you create, with that magnetic field around your wire, you basically create a magnet, an electromagnet. We call it a solenoid. Your solenoid has a north and a south pole, just like your normal magnets do. So it can, let's see, here's a picture. You can see how on the right is a bar magnet, just a natural, made of metal bar magnet. On the right is your solenoid. It's wire with electricity flowing through, and it has created, through that magnetic field wrapping around our wire, a north end and a south end, just like our magnet is doing. Now, I've put up a video in one of your tabs that shows how to create your own solenoid. It's not very complicated at all. It shows how to create your own solenoid and all of the fun things that you can do with it. So I encourage you to go after you do your notes and watch that video and have some fun with it. And make fun of their clothes, because it's like from 1980. It's kind of old. Alright, so the strength of our electromagnet, whether it's able to just pick up a paper clip or it's able to pick up a car, depends on the current that's flowing through it. And to increase your current, you can also, in addition to increasing your current, you can also increase the number of loops. The more loops you have, the stronger it is. And you can also place an iron rod, a nail, depending on the size of your solenoid. You place something iron, something metallic on the inside of that coil, and that will increase the strength of your electromagnet. Now, if we can use electricity to create magnets, the other is also true. We can use magnets to create electricity, and that's called a generator. Now, there's a picture of a very simple generator here. The ones that you would find at your electric plants are going to be much bigger and more complex, but the concept is still very much the same. You have some form of mechanical input that's turning this coil of wire, this loop of wire, inside a magnetic field. And the magnetic field is going to push those electric charges through the loop. And as you rotate it, it's going to push the charges this way, and then that way, and then this way, and then that way. And that creates what we call alternating current. I'm sure you've heard of alternating current, or AC. The opposite of that is direct current, like you would get from a battery. You have a negative end and a positive end, and it flows from one to the other, just one direction. That's direct current. And so the band name AC/DC is actually a group of electricians, right? So it's alternating current if it's flowing back and forth, like created with a generator. Direct current if it's like a battery flowing one direction. Now, I've also put up a video, in one direction. I've also put up a video that details how generators work, and on the flip side, how motors work, taking that electrical energy and turning it into mechanical. So that's kind of a fun contrast between the two. Finally, the transformers. We talked about this very briefly when we finished with electricity, but I kind of think it fits a little bit better with magnetism. Inside a transformer, you've got those big bucket-looking things sitting on the electric wires. You've got a coil, just like you see on your screen here. You've got a wire coming in to your coil that has many, many loops. That's the one on the left. And you have what's called a secondary coil on the right that has fewer loops. Your electric field coming in is going to put a force, a magnetic force, on the other set of wires through that iron core. And since the second set has fewer loops, fewer coils, than the first loop, it's kind of like your property of solenoids. More loops, you got more force. Less loops, you got less force. So that force, that potential difference, that voltage that's traveling through our wires is decreased on the right side from what it was coming in on the left. Now, that's more like what we see on our street corners, stepping down the voltage that is safe for our house to use. We want to step it down to that 120. At the electric plant, it's the opposite. We have fewer loops turning into more loops to step up that voltage, to give it the push to make it across the countryside to our neighborhoods. So, I think this part is really cool, how you use magnets to create electricity and use electricity to create magnets, and they just kind of work together based off of very, very similar principles. I told you it's getting sticky here. So that is it. This was a short section, but do remember that connection between the two. Magnets create electricity, electricity creates magnets, and we're about to go create dinner, right? Can you say bye-bye?
Bye-bye.
Bye-bye.